Hi, it's Sleepy Steve, helping you to fall asleep and study. Remember to subscribe to help Steve-O out, and I will keep making more sleepy stories. Tonight, we are going to close our Unit 3 motion journey by walking quietly through energy, work, and momentum in exam problems. Let your shoulders loosen. Let your hands rest. Let the day slow down a little. Physics can feel busy when the page is full of numbers, arrows, and equations, but underneath the working there are only a few very steady ideas. Energy is transferred. Momentum is conserved when the system is isolated. Forces can change motion. Graphs tell a story, and in an exam, your job is to explain that story clearly, step by step. Imagine a quiet school gym after the last bell has gone. A basketball rolls slowly across the floor. A spring in a small trolley launcher sits compressed on a bench. A stopwatch rests beside a meter ruler. Somewhere outside, the oval is almost dark. It is a calm place to think about motion because the objects are simple and the ideas are visible. When the basketball moves, it has kinetic energy. When a ball is raised above the floor, it has gravitational potential energy. When a spring is compressed, energy is stored as elastic potential energy. When a force acts through a distance, work is done. These are not just separate formulas. They are different ways of describing energy as it moves from one form to another. The first exam idea is work. Work is done when a force causes displacement in the direction of that force. If you push a trolley across the floor, your force transfers energy to the trolley and sometimes to the surroundings as heat and sound. If the force and the displacement are in the same direction, the work done is positive. If the force is opposite the displacement, such as friction acting on a sliding object, the work done by that force is negative because it removes mechanical energy from the moving object. This is a useful exam phrase. Work done by a force is the energy transferred by that force. In many VCE-style questions, students are asked to connect work to kinetic energy. The work-energy theorem says that the net work done on an object equals the change in the object's kinetic energy. This is powerful because it lets you solve motion problems without always finding acceleration and time. If a car speeds up, positive net work has been done on it. If it slows down, negative net work has been done on it. If its speed is unchanged, its kinetic energy is unchanged, even if forces are still acting. So when you read a question, ask yourself quietly, is the object gaining speed, losing speed, or keeping the same speed? Kinetic energy depends on mass and speed. The important word is speed, not velocity, because kinetic energy is a scalar. It has no direction. A car traveling north at 20 meters per second and the same car traveling south at 20 meters per second have the same kinetic energy. This matters in collision questions where momentum is directional, but kinetic energy is not. Momentum cares about direction. Kinetic energy cares about how fast something is moving. Now let us move to gravitational potential energy. When an object is lifted in a gravitational field, energy is stored because of its position. Near Earth's surface, we usually use the simple relationship involving mass, gravitational field strength, and height. In exam language, you can say that an object gains gravitational potential energy when work is done against gravity to increase its height. A book lifted from the floor to a desk gains gravitational potential energy. A roller coaster car at the top of a hill has stored energy that can later become kinetic energy as it moves downward. A common exam trap is to treat energy as though it disappears. Energy does not disappear, it is transferred or transformed. In an ideal system with no friction or air resistance, mechanical energy is conserved, meaning the total of kinetic energy and potential energy remains constant. But in a real system, some mechanical energy may be transformed into thermal energy, sound, or deformation. So if a ball bounces lower after each bounce, energy has not vanished. Some of the ball's initial mechanical energy has been transferred to the surroundings. This gives you a useful structure for written explanations. First, identify the system. Second, state whether non-conservative forces such as friction or air resistance are significant. Third, describe the energy transformation. Fourth, link the transformation to the change in speed or height. For example, as a ball falls, gravitational potential energy decreases and kinetic energy increases, so the ball's speed increases. If air resistance is significant, some energy is transferred to the surroundings as heat and sound, so the increase in kinetic energy is less than the decrease in gravitational potential energy. Now picture the small trolley launcher in the quiet gym. The spring is compressed. It is waiting. When the spring is released, elastic potential energy is transformed into kinetic energy of the trolley, and sometimes into sound and heat. Springs are useful in physics because they make energy storage visible. The further a spring is compressed or stretched within its elastic limit, the more energy is stored. In many problems, the spring constant tells you how stiff the spring is. A larger spring constant means a greater force is needed for the same extension, and more energy is stored for the same displacement. In an exam problem, a spring question often asks for the speed of an object after the spring is released. The calm approach is to write an energy statement in words before substituting numbers. You might write, elastic potential energy stored in the compressed spring is transformed into kinetic energy of the trolley, assuming energy losses are negligible. That sentence protects your understanding. Then the calculation becomes easier because you know what you are equating and why. If losses are mentioned, you adjust the energy equation by recognizing that not all stored energy becomes useful kinetic energy. Now let us turn gently toward momentum. Momentum is the product of mass and velocity, so it is a vector. This means direction matters. A small object moving quickly can have the same momentum as a larger object moving slowly. In collisions and explosions, momentum is often the most important quantity because the total momentum of an isolated system remains constant. An isolated system is one where the net external force is zero or negligible during the interaction. This is one of the most important exam phrases in this part of physics. Total momentum is conserved in an isolated system. That does not mean every object keeps the same momentum. Individual objects can gain or lose momentum. One object can speed up while another slows down. The key is that the total momentum before the interaction equals the total momentum after the interaction when external forces are negligible. Imagine two low-friction trolleys on a track. One trolley rolls toward another and they collide. During the collision, each trolley exerts a force on the other. By Newton's third law, these forces are equal in magnitude and opposite in direction. They act for the same time interval, so each trolley receives an impulse equal in magnitude and opposite in direction. This means the change in momentum of one trolley is balanced by the change in momentum of the other. The total momentum of the two-trolley system remains the same. Impulse is the change in momentum of an object. It can also be described as force multiplied by the time interval over which the force acts when the force is constant. This makes impulse a bridge between forces and momentum. If you want to change an object's momentum, you need an impulse. A large force over a short time can produce the same impulse as a smaller force over a longer time. This is why airbags, crash mats, and follow-through in sport matter. They increase the time over which momentum changes, reducing the average force experienced. In exam language, if a car crash barrier increases the time taken for a car to stop, the change in momentum is the same because the car goes from its initial momentum to zero. But because the stopping time is larger, the average force is smaller. This can reduce injury or damage. That explanation is stronger than simply saying the barrier softens the crash. Physics wants the chain. Same change in momentum, longer time, smaller average force. Now let us separate momentum from kinetic energy. Momentum is always conserved in an isolated collision, but kinetic energy may or may not be conserved. In an elastic collision, total kinetic energy is conserved. In an inelastic collision, total kinetic energy is not conserved because some kinetic energy is transformed into other forms, such as thermal energy, sound, or deformation. In a perfectly inelastic collision, the objects stick together after colliding. Momentum is still conserved if the system is isolated, but kinetic energy is not. This is another common trap. Students sometimes say energy is not conserved in an inelastic collision. That is not precise. Total energy is conserved, but kinetic energy is transformed into other forms. In VCE physics, it is better to say that kinetic energy is not conserved because some kinetic energy is transformed into internal energy, sound, heat, or deformation. This language is calm, accurate, and exam-safe. Let us imagine a simple collision. A moving trolley strikes a stationary trolley and they stick together. Before the collision, only the first trolley has momentum. After the collision, the combined mass moves more slowly. The total momentum before equals the total momentum after, but the kinetic energy after is less than the kinetic energy before. The missing kinetic energy has not disappeared. It has been transformed into other energy forms during the collision. A calm method for collision calculations is to choose a positive direction first. Draw a small arrow. Decide that right is positive, for example. Then write down the momentum before and the momentum after, including signs. If an object moves left, its velocity is negative. If it moves right, its velocity is positive. This prevents sign mistakes, which are one of the easiest ways to lose marks in momentum problems. The next step is to identify the system. If the system includes both colliding objects, then the forces they exert on each other are internal forces. Internal forces can change the momentum of individual objects, but they cannot change the total momentum of the system. External forces, such as friction from the track or a push from outside the system, can change total momentum. Many exam questions tell you to ignore friction or say the interaction occurs over a very short time. That is a clue that momentum conservation can be used. Momentum also appears in explosions. In an explosion, objects that were initially together move apart. If the system is initially at rest, total momentum before is zero. After the explosion, the momenta of the parts must add to zero, so they move in opposite directions with equal and opposite total momentum. A heavier piece may move more slowly, while a lighter piece moves more quickly. Again, momentum is vector-based, so direction is essential. Now let us connect energy and momentum together. Some problems require both. Momentum may help you find the velocity immediately after a collision. Energy may help you analyze what happens before or after, such as a trolley moving up a ramp, compressing a spring, or sliding to a stop. The secret is to notice the event type. During a collision, use momentum. During motion with height changes, springs, work, or friction, use energy. During motion with constant acceleration, you might use kinematics. The skill is choosing the model that matches the situation. For example, imagine a trolley rolling along a track and colliding with a second trolley. They stick together and move up a ramp. Momentum conservation can be used for the collision because it is a short interaction and external forces during the collision are negligible. After the collision, mechanical energy can be used to connect the combined trolley's kinetic energy to gravitational potential energy as they rise. If friction is ignored, kinetic energy after the collision transforms into gravitational potential energy. If friction is included, some energy is transferred to the surroundings and the maximum height is lower. This type of multi-step problem can seem intimidating, but it becomes manageable if you divide it into stages. Stage 1 might be before the collision. Stage 2 might be immediately after the collision. Stage 3 might be after the trolleys rise up the ramp. At each stage, ask what is conserved and what is transformed. Momentum is usually conserved during the collision. Mechanical energy may be conserved during motion if non-conservative forces are negligible. Kinetic energy may not be conserved in an inelastic collision. Graphs can also tell the story of work, energy, and momentum. A force versus displacement graph can show work done because the area under the graph represents energy transferred. A force versus time graph can show impulse because the area under the graph represents change in momentum. This is a very useful comparison. Force displacement area gives work. Force time area gives impulse. Both are areas under graphs, but they represent different physical quantities because the horizontal axis is different. If you see a force displacement graph for a spring, the area under the graph gives the elastic potential energy stored. If the graph is a straight line through the origin, the area is triangular because the force increases as the extension increases. If you see a force-time graph during a collision, the area under the curve gives impulse. A tall, narrow force peak and a lower, wider force curve can have the same area, meaning the same change in momentum, even though the average forces differ. Let us pause here and breathe. Work connects force and displacement. Impulse connects force and time. Energy helps us follow transformations. Momentum helps us follow interactions. In an exam, you do not need to panic when a question looks long. You need to ask which story the question is telling. Is it about energy transferred by a force? Is it about energy stored in height or a spring? Is it about two objects interacting? Is it about stopping time and force? Each story has its own calm pathway. Now let us practice the wording that helps earn marks. If a question asks why a falling object speeds up, you might say, gravitational potential energy is transformed into kinetic energy as the object loses height, so its speed increases, assuming air resistance is negligible. If air resistance is included, you might add, some energy is transferred to the surroundings as thermal energy and sound, so the increase in kinetic energy is less than the decrease in gravitational potential energy. If a question asks why momentum is conserved in a collision, you might say, during the collision, the forces between the objects are internal to the system and are equal and opposite, and if the net external force is negligible, the total momentum of the system remains constant. If a question asks why kinetic energy is not conserved, you might say, some kinetic energy is transformed into internal energy, sound, and deformation during the collision, so the total kinetic energy after the collision is less than before. If a question asks about an airbag, you might say, the airbag increases the time over which the passenger's momentum is reduced to zero. Since impulse equals change in momentum, the change in momentum is the same, but a longer collision time reduces the average force on the passenger. This is clear, causal, and exam-ready. If a question asks about a spring launcher, you might say, elastic potential energy stored in the compressed spring is transformed into kinetic energy of the launched object, with some energy possibly transferred to the surroundings if losses are not negligible. If the spring constant or compression distance is increased, more elastic potential energy is stored, so the launched object may have a greater kinetic energy and speed, assuming the mass is unchanged and losses are negligible. Now imagine leaving the quiet gym. The trolley has stopped. The spring is no longer compressed. The basketball rests against the wall. Nothing seems to be moving, but the ideas remain. Energy was stored, transferred, and transformed. Momentum moved through interactions. Forces acted over distances and over time. The world did not become simpler, but your way of reading it became calmer. For the final exam reminder, remember this simple decision tree. If a force acts through a distance, think work and energy. If a force acts over time, think impulse and momentum. If two objects collide or separate, think conservation of momentum first. If height, speed, or springs are involved, think energy transformations. If friction, air resistance, sound, heat, or deformation are mentioned, do not say energy is lost. Say mechanical energy or kinetic energy is transformed into other forms. And as you drift toward sleep, let the formulas become meanings rather than noise. Kinetic energy is energy of motion. Gravitational potential energy is energy of position in a gravitational field. Elastic potential energy is energy stored in a stretched or compressed spring. Work is energy transferred by a force through a displacement. Momentum is mass in motion with direction. Impulse is change in momentum. Conservation is the quiet rule that helps you follow a system even when the motion changes quickly. Sleepy Steve will leave the gym lights low now. The track is still, the spring is relaxed, the graphs have settled into their axes, the arrows have found their directions. You have finished another important part of Unit 3 Physics, and tomorrow, if you need to, you can return to these ideas one at a time. Energy, work, momentum, impulse, collisions, springs, and conservation. For now, just rest. Sleepy Steve wishes you a great sleep. Don't study too hard. Subscribe for more sleepy stories.